This is Felipe, and today I am in very good company with my teammate Pete to cover MongoDB versus ScyllaDB. Both databases are very different from each other, and by the end of this presentation, we hope you will get a clear understanding on how and when to consider ScyllaDB for your workloads. So, I am Felipe Mendes, and I work as a solution architect at ScyllaDB. I am also a ScyllaDB committer, having contributed with a few submissions to our open source project, and also one of the co-authors of our recently published Database Performance at Scale book, an open access, freely available publication with a focus on database on performance. All that said, Pete, why don't you just go ahead and please introduce yourself?
Hey, thanks, Felipe. Hello, everyone. I'm Pete Avon. I'm a ScyllaDB solution architect. I've been working, I started my career actually in software development for the first 10 years. And for the last 10 years, I've been a solution architect. But pretty much my whole career, I've been working with data and working with organizations with different databases to help solve business critical data problems, from everything from data modeling to application development. So it's a pleasure to be here with you today.
Thanks, Pete, and the pleasure is all mine. All that said, let's get started. So, guys, MongoDB versus ScyllaDB. Which one to pick? And there are many different ways to approach that question. But before we do, let's switch topics for a moment. Because, I am actually a big fan of social networks, and I mostly enjoy watching random videos during my spare time, which my wife, on the other hand, actually hates because I'm basically always immersed in those videos while she's speaking to me. So, today I brought you two of my favorite videos, and the first one, pay attention because it's really quick, is actually a demonstration that things that happen during an amateur football match around the Brazilian fields. So I'm going to play it and take a look at the defender. So he crosses the ball to the forward kicks the ball hits the post, the ball hits his head, and then it goes out. Then the match stops and everyone, of course, starts laughing at him because, how could he lose that goal, right? And the next video I brought is actually a more wild one. And when you live in nature, what's the number one survival rule? And you probably guessed it right. It is don't get killed. So in this video, we can see a snake approaching a cat, and then the cat quickly reacts faster than the snake, because as we can see, the cat's reaction time is much faster than the snake, which is pretty wild, huh? So, the videos which we just watched clearly demonstrate how fast your reaction time can save you from a life or death situation, or whether you are able to score a goal or not. Most importantly, we also believe that you will know when you need to react faster, either to overcome your competition or simply to survive in a fast, evolving, and changing environment. ScyllaDB is the database for high throughput and predictable low latencies. Our database counts with top-notch engineering advancements, allowing workloads to fully maximize the power of modern infrastructure. Our user space schedulers guarantee that background database operations never hurt your workload latencies, and our architecture was specifically designed to be always on, able to sustain even the most demanding mission-critical workloads. This results in extremely high performance numbers, even at lower node counts, which translates to lower TCO and direct savings for your organization. Therefore, the answer of whether you should go with MongoDB or ScyllaDB should be ultimately simple, and this is the mindset I want you to have for the rest of this presentation. If you care about performance, then ScyllaDB should be the solution of your choice. All right. Now we are past the basics. So let's start by understanding how ScyllaDB and MongoDB differ from each other, and what are the architectural differences among these two databases. So Data model and query language is perhaps the most well-known difference between the two databases. Starting with Mongo, documents are written to a collection, which is analogous for a table in relational databases by using MQL or MongoDB query language. Each document resembles the JSON format, which makes it fairly convenient and easy to get started from the developer's perspective, provided that JSON is a fairly common format used, in REST APIs, web services, remote procedure calls, and other applications making use of the request response model. Internally, these documents are actually stored on disk following MongoDB's binary JSON or BASON format, which stands for some MongoDB optimizations addressing some shortcomings within the regular JSON format, such as limited support for certain data types, for example. Documents in MongoDB are also schemaless. MongoDB does not enforce any particular set of fields to pre-exist before you add a new document. And although MongoDB does allow you to create validation rules for certain fields, this feature is entirely optional and not enabled by default. As a result of these decisions, MongoDB, data model, and its query language are characterized by favoring query flexibility over performance. Now, compared to MongoDB, ScyllaDB sticks with a totally different approach. First, we support two different query languages. You can interact with the database using SQL, the Cassandra query language, or you can use our DynamoDB API. Regardless of your query language of choice, you will interact with tables following a wide column representation. Here, the primary difference is that ScyllaDB tables do enforce a schema and require a predefined set of fields to be specified by your application when you interact with the database. By doing so, ScyllaDB is capable of efficiently storing and retrieving the data you're after and greatly improves the performance of your queries. As a result, ScyllaDB compared to MongoDB lives on the other side of the spectrum. That is, while MongoDB favors query flexibility, ScyllaDB focuses on querying performance. All right? So, the second major difference relates to the topology and deployment model differences within each database. The minimal production deployment of MongoDB is what we call as a replica set. A replica set will often comprise at least 3 nodes, where each node in the cluster has a specific role, a primary or a secondary node. Primary nodes receive all writes operations, and no writes can be routed directly to secondary nodes. Reads, on the other hand, can be directed to either primary or secondary nodes, depending on your consistency requirements. Although most MongoDB drivers default to reading only from the primary node, but that's configurable. So this architecture introduces a set of problems detrimental to performance. First, because writes are accepted only by the primary replica, it means that the single replica may be unable to keep up with the incoming pace of requests, and thus become a bottleneck. Second, it also introduces high availability concerns, because whenever your primary node fails, the database will require electing one of the secondaries to become the new primary. Until that process completes, you will be unable to perform write operations to your MongoDB deployment. So to address some of these shortcomings, your intuition might say, okay, so let's just add more primary replicas then, except that you cannot. By definition, a replica set can only have a single primary at a time. And speaking of adding more nodes, there is very little reason to actually scale a MongoDB replica set, as adding more members will only provide increased fault tolerance to your deployment. For example, in a replica set with 3 members, your cluster can only tolerate the failure of a single node. With 5 members, you can tolerate the failure of up to 2 members, and so on. One possible reason to scale out your replica set is to have a deployment spanning across multiple regions. Still, a single replica set has a limit of up to 50 members. And as you scale, as you add more and more nodes to your replica set, it ends up introducing additional configuration complexity, such as nodes with specific roles, arbiters, and no voting members. The name replica set actually steers down from the fact that adding more members to it won't spread or shard your data. In other words, all members within a MongoDB replica set will eventually hold the very same data set. So actually, the question we should be asking is, and one of the things we need to realize is that if one of your replica set members ends up with limited storage space, you have no option but to actually increase that node disk space. However, there is a catch here, which is you cannot add disk space indefinitely to a node. And if you look into MongoDB Atlas documentation, for example, you will notice that a single member, a single node, and thus an entire replica set can only hold up to 3 terabytes of data. So the question is, what if you need to store more than 3 terabytes of data in a single replica, in a single MongoDB replica set? Well, if that's your case, then you will be introduced to the wonderful world of MongoDB sharded clusters. And in a nutshell, a MongoDB cluster is basically a collection of replica sets where each replica set is a shard. And this topology introduces additional components such as query routers and additional configuration servers, which hold internal metadata details about your topology. Therefore, it introduces additional latency overhead, because now you no longer query your primary or secondary nodes directly, but there's the query router, this main here in the middle instead. And this topology also, of course, introduces more complexity, as now you have more components to manage. So a sharded cluster, similarly as a replica set, cannot scale indefinitely. And MongoDB today has a hard limit of 12 shards for a multi-region deployment, or 50 for a single region. MongoDB sharded clusters prevent you from fully utilizing your full cluster capacity. We have already discussed how the primary-secondary model isn't great for write-intensive workloads, but even if you have a read-intensive one, imagine what happens if most of your read requests end up overwhelming a specific shard in your cluster. In this case, the remaining replica sets won't help you distribute that load, and you will end up with bad performance and underutilized resources. Finally, in MongoDB, data sharding is done manually. You can choose from either a hash or a range-based sharding approach, and then your MongoDB query routers will be responsible for correctly routing your requests to the appropriate shards in your cluster. In the end, introducing sharding to MongoDB turns out to be redundant, because you will need to run through the exercise of properly selecting a good sharding key, and by doing so, you not only sacrifice some of the flexibility features present in its query language, such as consistent indexes, for example, but you may also incur an even higher performance hit, particularly when some of your queries need to traverse through multiple shards in order to satisfy your query restrictions. All right. So, how does a ScyllaDB deployment compares with MongoDB? Well, in ScyllaDB, all nodes are equal, and there are no particular roles such as write-only or read-only replicas. All nodes can serve requests equally, and load balancing is transparently handled by your application drivers. Sharding is built in within ScyllaDB's architecture. As I previously spoke, we do require you to select your keys, your sharding keys beforehand, and data gets distributed not only on a per node basis, but on a per CPU basis. Hence why we have a shard per core architecture. Shard per core, guys, is not only about sharding, but also about fully maximizing your underlying infrastructure. When you deploy a ScyllaDB cluster, each CPU has its own dedicated portion of memory and I/O resources, such as disk and network access. Um, the ScyllaDB architecture was made from the ground up to scale indefinitely and support non-stop mission-critical operations. For example, if you need more capacity, then guess what you have to do? You just go ahead and you add more nodes. That's simple. Really, there is nothing else to speak about it. Simplify deployments and reduce management. When a node fails, you just replace your failed node with another node. No need for us to reason about elections whatsoever. Your drivers will autonomously know a specific replica in your cluster became unavailable and will route queries to other available nodes within your ScyllaDB cluster. Uh, Now, how does ScyllaDB compare with MongoDB? Does a performance-oriented architecture win over a flexible one? So Benchant went to seek those questions, and what Benchant did is that they ran a whole suite of tests over distinct workloads and access patterns comparing both databases. As a result of their testing, ScyllaDB outperformed MongoDB in 132 out of 133 measurements. And Benchant also tested how much ScyllaDB and MongoDB compare on scaling. So you've probably heard that MongoDB is web scale. And if you haven't, I highly encourage you to Google it. But is it really? Well, according to Benchant results, it turns out that not really. While ScyllaDB shared per core architecture achieved near linear scalability, MongoDB fell short. And put simply, scaling a MongoDB deployment results in higher costs with very little performance gains. Now, these are just the basics over the differences between MongoDB and ScyllaDB, but Pete, I would like to call you now. What if I am currently running MongoDB today and I'm facing performance problems? What should I know beforehand, and how can I shift over to ScyllaDB?
Hey, thanks, Felipe. That was a lot there. So before we go into this, I just want to touch base on a couple of things you were pointing out. So I've been working with databases for 20 years, and databases are purpose built for different types of use cases. And so Mongo, right, was really purpose built for developer productivity. We can stand up an application really quick, and we can get some applications in front of the users. But those applications, they aren't able to scale, right? And Scylla is purpose built for performance and for scale, right? And that's one of the key differences here. And I love that overview. What happens with databases over time is people start developing applications. They start, they're excited about the database they're using and they're getting things done, but then they need to scale and they start going through all those gymnastics like you were showing with replica sets and sharding. And that's not unique to MongoDB. You'll see that relational databases as well. But you didn't even touch on the fact that like backups, what do those look like? Things become a nightmare when you're manually sharding in any system, right? But Scylla simplifies that with our massively scalable parallel architecture. But you're going from Mongo to Scylla. Last thing, it's not an all or nothing proposition. I know you're going to touch on that later, but essentially it's like, hey, what are those use cases where we need that performance, we need that scale? When we need to move to Scylla, we're going to move some of our workload from Mongo to Scylla, and what does that look like? And so I'm going to touch on some of that here in these migration options for us. And just to be upfront about it, it's a simple matter of programming, right? so these systems, there is no ETL tool, there is no data movement tool to go from a document database to a wide column store, right? So you're going to be doing some programming, but that's okay, right? The thing is when it's all about what's the pain we're trying to solve, And when we have business critical applications, we're not able to scale, we're not able to provide answers to capture information from our users or systems and provide answers back to those users and systems with single digit P99 latencies like Scylla does. We start looking at those workloads, and it becomes important to the business to move those workloads to Scylla, right? And so people are willing to do that because we're solving a business problem, right? You'll find Scylla in all sorts of business critical applications. But moving from Mongo to Scylla, it's not like there's not a tool to do this. You're going to have to put some thought into it, right? And it's going to start with your data model, essentially, right? So, but for the programming, just to let you know, connecting to Scylla is easy to do. You touched briefly on our shardware. We have a shardware architecture. Essentially, we have shardware drivers. So Scylla is completely compatible, like you noted, with the Cassandra ecosystem of tools, as well as DynamoDB, the AWS CLI, and all the AWS SDKs for Dynamo. But we have our own drivers as well, which are more optimal for working with ScyllaDB. And so we have shardware drivers for Python, Go, C++, Java, and Rust. And we also have Spark and Kafka connectors, right? And these are where you're going to start moving your data over from Mongo to ScyllaDB. And so when we start with the data model, I got ahead of myself there, right? We can think of collections versus tables. You touched on this. So collection is a group of documents in the Mongo, right? And so we have these documents on the left like name, age, status, groups. And we move them to Scylla, we're gonna put those into a wide column table format. So how do we get from here to there? So here's a mental exercise, right? This is just something we made up that's a little novelty to it because everyone likes memes. And let's say we have a business critical application that serves memes. There's probably some ad tech involved, right? Or something that people are doing this for. But we have two collections here, one for meme group and one for memes. And there's some overlap here in the attributes, right? But we're coming from the document world of, these JSON documents or BSON documents where we have IDs for the different types of meme groups and tags associated, pointers to photos, particularly maybe on another system or on S3 bucket somewhere, the views, the likes. We have another group for memes, right? But we have a couple of questions we want to be able to ask. And this is what it's like when you start with NoSQL. When you start from Mongo, don't start thinking about, I've got these documents, and then how do I necessarily move them over to a table format? I mean, that's the thought that's in your head, but there's no necessarily any tool or framework to follow. Like, documents like this are documents with this shape will look exactly like this in a wide column store. No, you need to start by asking yourself, what are the questions I want to ask of the data, right? What are the questions? What are the answers I need to get from this data? And then we're going to put that data into that shape within Scylla, right? So we think of the things like display all memes posted by a given author sorted by time. What would that look like? What data do we need from those collections? How would we put that in Scylla? We want to retrieve all groups of memes matching a particular tag. What would that look like, right? I'm actually going through this exercise with another company right now that's coming from Graph, and it's very similar. They're coming from a Graph mindset, and they're having to rethink like, okay, we've got the data, but how do we put that data in an optimal shape in Scylla to be able to answer the questions we want to answer? And it starts with, what are the queries? This is different from traditional data modeling, right? In traditional data modeling, your third normal form and relational tables, you just sort of, there's a rule for that. We normalize all the data, and in the NoSQL world, we model the data first, then we write the queries in traditional database modeling. In the NoSQL world, we think of the queries first, and then we model the data to shape the queries, right? And so that's what we do here. So following our mental exercise, display all memes posted by a given author sorted by time. We look at the table, on the left, create table meme by author, and we've got our author and our meme IDs and our post times and our title text and some tags. We have a primary key, and for those familiar with Scylla, we know that the first author is going to be our partition key, and our post time is going to be a clustering key, and essentially those times will be sorted in some order. So assuming we know the author, we can go grab everything from that author with everything already sorted by time for us. And on the right, we have our create table meme group with a group UUID, author ID, title text, another primary key. We've created an index on meme group tags, right? So this is, we're doing this in a nutshell style within 20, 30 minutes within this presentation. But when you look at data modeling in Scylla, essentially what you're going to do is it's going to hash based on the partition key. You don't have to think of the shard key necessarily, right? You're thinking about our partition key, essentially what's the most important attribute here that I want my data to be distributed by. For on the left, it's the author. On the right, it's the group ID. But this is going to be the partition that's going to end up on a node, and everything associated with that partition by that key is going to be available. And when I make my queries, I want to go to that particular partition and get that particular piece of data. Additionally, though, I can sort things on that particular partition by adding an additional index like we do here for tags. So for my tags, I might want to be able to, essentially search within those tags to find a particular set of, a group by those tags associated, right? By our particular tag. Now, this is adapted from a Stack Overflow exercise, and so we've made the link available in the query. Now, this is what's going to start, and this is what you're going to see if you Google this and you look all over the internet, but I'm going to tell you hey, in reality, the practicality, it can sometimes look a little different. So ScyllaDB has JSON support, and certainly all the examples you're going to see are going to start with taking a document and taking the attributes from that document and making them into columns, essentially turning it into a table and making it columns and rows in Cassandra or ScyllaDB, right? And so with JSON support, you can say insert into my table JSON, and you can pass the JSON, and those attributes will automatically be allocated to the proper columns, right? So we select ScyllaDB supports select and insert statements, and there's actually a couple of functions to JSON from JSON to be able to work with the values and the attributes of the data in Scylla. But it doesn't always look like this. For some use cases, it depends on the queries, depends on the data and what you're trying to achieve. And all the examples start with this one, but sometimes it looks as simple as this, right? Assuming I know my key, assuming I have a key that, hey, makes essentially a bucket. Well, what's my bucket of information I need to go grab? I could just stuff the JSON into a column and just go grab, go retrieve documents based on their particular ID, right? You can leave the JSON as is. Now, it doesn't look as drastic as this. Essentially what we see a lot of is you extract out of the document a couple of the key attributes for your partition key, your clustering keys, for the types of queries you want to answer, so you can go retrieve those pieces of information really, really quickly and leave the rest as a document, essentially serialized as JSON in a particular column. Usually there's a hybrid approach to this, right? And so with this hybrid approach, I can quickly say, we're following in this example, following the examples throughout. This is basically movies and with directors and titles and years, but assuming my application allows me to say, hey, I want all movies by a director for a certain year, I can go grab the document, and the document can have all sorts of information in it, and I can go essentially deserialize that in my application code, right? So it's not always just, hey, take the document and turn it all into rows and columns. Sometimes usually you'll see more of a variation in a hybrid type approach. Now, doing that, again, you're going to be doing that first, what you're going to do is you're going to ask yourself your question about what are the queries I want to be able to, ask of the data. I'm then going to create tables to support those types of answers. And then I'm going to move that data over, using my connectors and my drivers. But before migrating, you want to understand the differences between a document versus wide column. So denormalize and design a query-driven approach. You optimize your model for fast retrieval and ingestion, and you take the opportunity to reevaluate your access patterns. So test, right? It's always good to put representative data in the system, you essentially and test your theories. See if you're able to get the answers you want, and you're getting what you want to be able to get out of the queries and the system. Scylla, what's wonderful about Scylla is if you're familiar with Scylla monitoring, as you write your queries, you can actually go and you can see actually what the SQL is doing and if your data is distributed evenly and what your access patterns are. You can actually see that through our monitoring tool. And this will give you hey, I'm on the right path. I'm going the right direction. This is when I load more data, do some more testing. You'll have a lot of confidence leveraging Scylla monitoring to gauge your approach. So get to know the available data types, indexes, collections, and UDTs in ScyllaDB. And implement highly concurrent asynchronous code in your application. So what we mean by this is, in this NoSQL world, it's okay to duplicate data across tables. It's also, the idea is when you ask a question of ScyllaDB, you do not want to ask like a question where Scylla has to ping pong all around the system and go to different partitions across different nodes to get the information. Assuming you know you have some bit of information that tells you about the partition that data is on, it's better to essentially blast 10 concurrent requests and let those requests go to their particular partitions and get that information back very quickly, aggregate it in your application code, as to try and in ScyllaDB we don't do joins in ScyllaDB, right? You demoralize, you create a few gigantic tables, you distribute it across partitions across the system. If you're doing things right, you're going to your particular partition to grab the information based on your partition key, and when you're doing that, you're going to do this concurrently, right? And it's better to blast multiple requests as opposed to one request that's trying to do a lot of joining in the database. ScyllaDB is not built for that. But blast ScyllaDB with these concurrent requests, and it'll handle it, right? So we're talking about millions of ops per second, right? So hundreds of thousands to millions of ops per second. And again, you can watch that in Scylla monitoring, which is fun. It's excellent. So here's a little bit of a migration walkthrough, what this looks like in action. We have a MongoDB application. It's been great, but it's not scaling. We're running into all sorts of problems with these shards and these replica sets, and we can't get the scale, the performance we want. So we're going to take some of that workload, or actually this particular workload, and we're going to move it all over to Scylla. So MongoDB has chain streams, and the first thing we can do is we can start taking some of those, we can take the Kafka connector and start connecting to those chain streams to grab, the live data that's actually happening in our MongoDB application. Additionally, we have our Apache Spark connector. And so we can forklift historical data and do some ETL using Apache Spark and move that over to ScyllaDB, while we have our Kafka connector essentially pulling the data from those MongoDB chain streams. And once we get that data all over to Scylla, we can then just redirect our application and point it to Scylla. And we no longer have to, this is how you do it essentially when you have a dual. This is one way to go over to migrate from Mongo to Scylla, right? Of course, your mileage may vary. Sometimes your application is doing dual writes to both Mongo and Scylla, but this is the 101 in a nutshell. How to migrate an application from MongoDB to Scylla. So now, essentially that's the in a nutshell version of migration. That we could have gone deeper on so many more of those topics. I hope that was useful as an introduction. But I think what will help understand this more is some of the success stories, some of the organizations who have done this and put this into action. And Felipe, you got more to tell us there?
Thanks, Pete. So yeah, we definitely still have a lot to discuss, and let's get started by discussing some of the users who actually successfully migrated from MongoDB to ScyllaDB. And in case you were guessing, you probably guessed it right. First runner up is Discord, and in case you didn't know, Discord actually started with MongoDB in 2015. At the time, everything intentionally ran on top of a single replica set and scaled to hundreds of millions of messages. So Discord knew at the time that they would need to eventually switch off from MongoDB, as introducing ScyllaDB sharding would be very complicated to use and not known for its stability, at least at the time, which still is required for their mission critical platform. In 2016, Discord completely switched to Apache Cassandra, which allowed them to scale from hundreds of millions of messages to billions of messages. And 3 years later, they were at ScyllaDB Summit presenting on how Discord migrated trillions of messages to ScyllaDB. Now, if you ask me, trillions is definitely an impressive number. But what I find even more impressive is that ScyllaDB supports that magnitude of scale while reducing their deployment size by 60% and keeping their P99 latencies at single-digit milliseconds. So at this point, this is the Discord story, but I know what you're probably thinking. So guys, Discord is too big for me, or I'm not into that level of scale yet. And believe me, Pete and I, we hear this sort of statement far more often than we actually would like to. So if that's your case, you're not in a scale as Discord currently, consider Traction then. A startup which, similarly as Discord, they also started with MongoDB for iterating quickly and eventually reached out a tipping point where the latencies became unbearable. Traction's story teaches us an important lesson. They knew that they needed a highly scalable and highly performant NoSQL database, which alludes back to what we spoke during the beginning of this presentation. I have personally worked very closely with Traction during their adoption and implementation of ScyllaDB. And Traction also, similarly as I just posed the question to you, they also thought that ScyllaDB would be an overkill for them. At the time, I recall I told them, listen, guys, ScyllaDB may be an overkill to you, but as I can see on your metrics, you are already struggling with MongoDB. So why don't you do this? Deploy a small ScyllaDB cluster, start small, and then rest assured that you will have a database built for the scale along your growing needs. So Traction, they really liked the idea at the time, and they conducted their own MongoDB versus Postgres versus ScyllaDB benchmarking. The results have shown dramatic latency improvement, as we can see in the right side of this slide. And Traction was a small startup when I met them. And today they have already scaled their deployments to larger instance sizes, and they're soon to onboard new use cases to ScyllaDB. We then get to Numberly, and their story tells us, and Pete spoke about it, sometimes, ScyllaDB may simply not be a good fit for your use case. Every database has its own, is suitable for to handle one specific problem, right? So Alexis Jacob delighted us with a very detailed talk back in 2019 and explained that they are actually happy users of both databases because what did they do? Numberly, they primarily select the database for a particular use case based on each database's strengths. Alexis explained, for example, that they stick with MongoDB for the unpredictable data they receive from their users. For example, imagine third parties feeding your systems with their own data, which do not necessarily follow the same schema. They still would like to query and operate on top of that data. And this is when MongoDB query flexibility is more important for them. Conversely, their latency-sensitive pipelines, batch, real-time processing, and backends which impose a schema all go to ScyllaDB in order to fully benefit from our core database performance. So now, Numberly teaches us two important lessons. First, in the end, guys, there is no real winner here. The best database is the one which best fits your use case requirements. And second, and Pete also alluded to that, a clear understanding of where you want to be and your use case details is what primarily matters when choosing a database. So, this is what me and Pete had to present. You can find our contact details here. We hope you enjoyed it. Pete, any final words for our audience?
No, thanks, Felipe. Great working with you.
Awesome. Thanks, guys, and hope to see you soon. Bye.